All right, so electromagnetic waves. So I could have made you do a pre-quiz, but I decided not to. So, electromagnetic waves. They are electric fields and magnetic fields that are oscillating perpendicular to each other. And I'll write this down, what you want to write down. But so, oops, wrong computer. Okay, so looking back to electromagnetism, foundational fact number 3 said if a conductor experiences a change in magnetic field, voltage is induced across that. Okay, I'm just kind of throwing that out there. If we dig a little deeper, we find that if a magnetic field is changing, it actually induces or creates a changing electric field. And the crazy thing is, the flip side of that is an electric field, a change in electric field, induces or creates a changing magnetic field. But didn't you just say that a changing magnetic field creates a changing electric field? Yep. But a changing electric field creates a changing magnetic field. Yep. But what? They create each other. They self-induce each other. Okay? And this is how an electromagnetic wave can travel through space. It doesn't need a medium. It's self-perpetuating. Okay? And so you've got an electric field in a wave, and you've got a magnetic field perpendicular to that because of the right-hand rule, and they're doing this through space. Okay? And you could take this to the dance floor, like, yeah, call that the EM wave. Be that cool. Okay? So you've got an electric field and a magnetic field. They're perpendicular to each other. I don't know if you can see that, how well you can see that, but good with that. Okay. So here are some characteristics. So you have an electric field. They are electric field and magnetic field. Oscillating perpendicular to each other. They don't need a medium. Which is good because they can travel through space. If this wasn't the case, we would not receive any light or warmth from the sun. Game over. Okay. Good at that. Okay. Yes, they can travel through space. What is the speed at which they travel through space? Um, they travel at the speed of light. Speed of light has a special variable. It's lowercase c. It's 3 times 10 to the 8 meters per second. That's how fast electromagnetic waves travel. Speed of light. Okay. Now, these are waves. Remember this equation? Speed of a wave is equal to frequency times wavelength. Okay. When we apply this to electromagnetic waves, the speed is fixed at 3 times 10 to the 8th meters a second. Cool with that? Okay. This equation, you use this in chemistry. You might not have realized it when you did spectral lines, like the colors. Okay. You use this equation. So this is a special case for this equation applied to electromagnetic waves. Good there? Okay. All right, so let me introduce you to electromagnetic spectrum. So here, all these waves move at the speed of light. Okay, and there are a whole bunch of different wavelengths and frequencies. Okay, is this a long wavelength or short wavelength? Long. So is that going to correspond to a high frequency or low frequency? Low. Okay. Over here, you're going to get short wavelength, but high frequency. Everybody see that? Okay. This side's fixed. As this goes down, this goes up. Okay. So long wavelength, low frequency, short wavelength, high frequency. Okay. And the wavelengths, the spectrum of this is crazy. You got wavelengths that are longer than a football field, all the way to wavelengths that are the diameter of an atom. Sorry, the diameter of the nucleus of an atom. It's crazy spectrum. Okay. So we have categorized these in 7 different buckets of, which kind of labeled them. Okay. The boundaries between the twos are a little fuzzy, but you have radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. You don't necessarily need to have those memorized, but you do need to be able to recognize, hey, that's an electromagnetic wave. That's part of the spectrum. Is a microwave an electromagnetic wave? Yes. Which has a longer wavelength, microwave or X-rays, something like that, Okay. So we're going to take a tour of the electromagnetic spectrum. First off, radio waves. Okay. So obviously you've got your radio frequency, like your radio stations, your AM, FM, the different stations that you turn to are actually like 98.8 or whatever is megahertz. It talks about the frequency that you're broadcasting. Okay. Um, AM has a lower frequency, longer wavelength than FM. Then you have XM. You have different like military uses of this. TV signals are in the radio wave category. Um, Talking to satellites, that type of stuff. All that stuff is in the radio wave category. Okay. Next up, you have microwaves. Now, we can talk about this for a while. So, so first off, microwave ovens, obviously a connection there. Cell phones also use microwaves. They're like, ooh, wait a minute. That seems weird. So the way microwave ovens work is they're designed to emit electromagnetic waves that are the same frequency at which water molecules resonate at. Okay, so you remember the demonstration that I had with the two tuning forks right here, and I hit one and it caused the other one to resonate. Okay, and then I made one a different note, put in that ballast, hit it, and it didn't resonate that one. Okay, the frequency at which water molecules vibrate is like 24 gigahertz, 24.5 gigahertz, or something like that. Okay, that is just one frequency in this category of microwaves. Okay, if you don't have that specific frequency, you're not going to cause water molecules to vibrate. Okay, so I don't know if you've noticed, but like when you cook something in the microwave, dry things don't work out very well. Like you need to add water to it because it's honing in on those water molecules. Okay. Now, if you were to stick your head in the microwave oven, that would be bad. You're mostly water. Okay. But if your cell phone and other devices are emitting microwaves in this broad category, but if they're not right at that resonant frequency, you're fine. It's not going to resonate water molecules. Okay, so that they cause electric. So tinfoil is a conductor, and so that gets those electrons moving because it's a sea of electrons that are like able to move. And so any type of conductor, you're going to get this skinning effect circuits going on. It's not good for your microwave, but it's causing current. Actually, I'll pick that up here momentarily. Okay, so all these other things, Wi-Fi, Bluetooth, radar, all these, and cell phones, all these other things fall within this category, this big category of microwaves. A lot of people asked me when we were doing electromagnetism, hey, how does wireless stuff work? This is how it works. So is that why when like calls can't go through? Is it because there's too much interference with each other? Great question. A lot of times it's there's too much traffic, like too many signals coming in. Like if something happened, like, hey, we're having a tornado, everybody's getting out their phones. Mom, you have a tornado, and it gets overloaded. The system gets overloaded. That's largely why. I mean, there's other reasons, like a tower could go down, or like there's you're like deep in the basement, so that the microwaves can't get out through like some thick concrete or something like that. Because when you're really high up, it doesn't really work unless you got a special phone, I think, or like, and so it kind of drains your battery. They also said it's like uh, there's a chance that your cell phone frequency can interfere with the communication with the pilot and the ground. So it's like, just turn it off. It's kind of an easy rule to have that eliminates the small chance of. At least that's what I've been told. I don't know that specifically. Okay, so um, the way wireless anything works is you have an antenna that is a transmitter. So it has electrons in there vibrating up and down at a certain frequency, and they create an electromagnetic wave in the microwave region. And that goes speed of light to your device. So from your phone, Bluetooth connection to your AirPods, there's a antenna in your AirPods that when the electromagnetic wave hits it, it causes the electrons in there to vibrate at a certain frequency, at a certain like, and that's how that information is transferred versus wires, like just alternating current. It converts it from alternating current here in your phone to electromagnetic waves and then back to alternating current once you get to your AirPods. Does that make sense how that works? Okay, so that's Wi-Fi. Bluetooth. Bluetooth is for smaller, closer connections. Wi-Fi can go further, but these are all in a microwave region. Some people say that cell phones work on like high radio frequencies. The boundary between radio waves and microwaves is kind of fuzzy. Okay, in my opinion, when your kids are taking physics, I think we'll subcategorize these things into smaller categories because there's just so much technology in this that's just exploding. Uh, if you're not sure what you want to do with your life, this is definitely a field of that has lots of applications, lots of like wireless transmission of stuff. Like you got a job like that, easy. Okay. Radar is also in that. Okay. Next up is infrared. So infrared, probably the most common application or like evidence of that is it's associated with heat. Okay. Anything that's above absolute frequency, sorry, absolute zero, emits infrared waves. Everything's above absolute zero. So everything's emitting infrared rays. Okay. And so you can get a camera that's sensitive to that to pick up and get thermal imaging. It's like how Predator sees. It's kind of a historic reference. But you can use these thermal imaging cameras to like figure out where you're losing heat from your house, like look to see which circuits are working versus not. Look to see pipes that are clogged, like you can put hot water down here and see where it stops getting hot. You can see living things at night, a lot of different things. Okay, so that's infrared. Also, um, infrared is works with remote control stuff. So, see this light bulb? See it flashing? Nope, because you can't see infrared. Okay, but check this out. Your camera can. Okay, it's a light bulb sending a flash of infrared. You can't see it, but things that have infrared sensitivity can. Okay, so all remote controls work that way. Andrew. I think right there. Oh, let's see if you guys can see this. Oh yeah, totally. That was easy. Okay, good with that. All right. Next up is visible light. Uh, this is the part of the spectrum that we can see. This is your Roy G. BIV. I don't know if you've heard of that acronym. Red, orange, yellow, green, blue, purple, indigo, violet. Personally, I'm a big fan of like the Crayola colors, Roy G. BP. Just like this indigo thing. Like, here's where this came from. Newton, back in the day, evidently there were 7 notes to the scale, music scale, and he's like, there's 7 notes, there should be 7 colors. And before that, orange wasn't a color. They didn't say, it was red, yellow, green, blue, and they're like, nah, orange is kind of just like orange, yellow. So it's like it's arbitrary where we draw these lines. I mean, look at your Crayola color box of like the 64 pack. Like, so anyway. All right. Ultraviolet UV rays. These are commonly associated with sunburns. Um, so this is like skin cancer stuff. Um, bugs can see, some bugs can see into the ultraviolet region. Okay. So here's something cool. Oh, no. All right. You see, okay, first off, frequency is proportional to the energy carried by the waves. The higher the frequency, the higher the energy. Directly proportional. Okay. So as we go this way, we carry more and more energy. Do you see this thing in the background here? Okay. These electromagnetic waves in this region can get through our atmosphere. Okay, so you got a big section of radio waves that get through our atmosphere. This is why we use radio waves to like try to find other life forms in our universe. We can transmit and receive radio waves. Okay. Infrared gets through, which is really nice because that's where we get warmth from our sun. Visible light gets through. That's really nice because we can see stuff outside of our atmosphere, like everything else that exists. Okay. The specific frequency of water resonating, all this other stuff gets blocked by our atmosphere. The part that gets blocked is like the resonant frequency of water gets blocked. Good thing. Okay. From here on, all these electromagnetic waves give us cancer because it carries more energy. All of these waves get blocked. Majority of them get blocked by our atmosphere. Yep. Okay. It's a really good thing we have our atmosphere. let's try to take care of it a little bit. Just throwing it out there. Okay. Okay. Next up is X-rays. Okay. Obviously, we've been to the dentist office. You get X-rays. You've got cavities. You broke a bone. Um, so these are more energetic. They can give you cancer over time. Um, this is why you wear a lead smock, where they put lead blankets over you to protect you from that radiation, the electromagnetic waves of X-rays. Okay. Now, they told me when I was in there, I was like, "How much is this?" And they told me, "Well, it's about equivalent to how much uh, radiation you get from playing outside on a sunny day for a whole day." I don't know if that's entirely true, but that's what I was told, so I'm just going to go with it. Um, my guess is that's true with the lead smock. Like, you wouldn't want to do that without, like, um, so quick little lesson on how X-ray machines work. Um, so the camera is the receiver, is like the catcher. If you're playing catch, the camera is the catcher of the light, of the X-rays. the the thing that shoots out X-rays is behind. It's what you're placing your hand on or what you're lying on, and it shoots X-rays through your hand. And the camera is the catcher of that, the receiver of that. Okay, this is actually an X-ray photograph. So the X-rays pass through the soft tissue and can't get through the denser bones. This is actually an X-ray photograph. We take the negative of that to see the actual X-ray to see if a bone's broken or see if something's whacked out or cavity. Okay, so, does that make sense? Like, it's the inverse of that. Okay. And lastly, you get gamma rays. Okay, this is what is notoriously associated with radiation. Sorry. And an MRI is totally. That's that's not. Yes. 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 Yeah. MRIs are not X-rays. No, you're fine. You're fine with that. MRI is magnetic resonating imaging. It it measures the magnetic field produced by your molecules, and they're different. It's crazy. They do it a whole bunch of times, several layers. Like, they take slices. Take zzz, 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 zzz. Yeah, it takes a long time. Yeah. Okay. So this is this is the highest level of energy. This will give you cancer, give you like 3 eyes and 5, like, grow an extra arm or something. Like, this is the Hulk stuff. Like, this is what all the Avengers got exposed to. Um, okay, this is the stuff with nuclear fallout, all that stuff. Geiger counters, radiation. Technically, radiation is, in a science terminology, all electromagnetic waves are radiation. We just associate this stuff with the cancer-giving radiation. Okay. So if you could see, if your eyes were susceptible or perceptive of the different waves, this is what our sun would look like. This is what the sun looks like from radio waves it gives off. Now they added color just for, like, coolness effect. But radio waves, microwaves, infrared, visible light, they should have made that at least yellow. That's kind of funny. Ultraviolet X-rays are crazy. This is what our sun looks like in terms of what it emits gamma ray wise. Okay. And then this is, if you took a photograph with a thermal imaging camera, infrared that's reflected, visible light, ultraviolet that's reflected, and X-rays. Okay.
So asking about space.
Yeah.
So do you just see things like outside our things reflecting back, or because I thought you can only see it because of our atmosphere.
Okay. So say that again. So if you're outside of our atmosphere, can you see other things?
Well, I know that you can see other things, but like, how would that work? It's just because there's no, it doesn't need medium or something. Never mind, it's okay.
Okay, so we can see everything. Our visible light gets through. So everything that we see on Earth, we can still see in space. What we are exposed to outside the atmosphere is a lot more violent. Like that's why you need a spacesuit. One of the reasons you need a spacesuit, because you're not able to see anything because your sight is just this little skinny band right here. You're exposed to all these things, um, but good with that. Okay. Like if you could see into the like especially microwaves, this room would be filled with light. Like it's just because like cell phones, Bluetooth, like routers, like all this stuff. It's crazy. Okay. All right. So the last thing. So electromagnetic waves are another example of a wave. All the characteristics and attributes of waves, light also demonstrates. So scientists, astronomers were looking at the stars, and they know what the stars are made out of, and they're looking at the spectral lines. Remember in chemistry when you looked at the light rays, and you had like the red and the violet, the purple, and then you had these lines or something like that, and you can identify, oh, here are the frequencies of light and stuff. Okay. When they looked at stars, they're like, these should have this signature. It turned out that they were slightly shifted towards the red side, to the left. They're like, what's going on? They recalibrate their instruments. They did it again. Over time, they're like, well, this is weird. I'm pretty sure we know what these things are made of. We're pretty sure that these should. So why would this be causing this? Like, what could be a possible explanation? And over time, they're like, the stars, these galaxies, they're moving away from us. They're experiencing a Doppler effect. Their frequency is lower than what it should be because the source of, instead of sound, is the source of light, is moving away from us at a fast rate. And that's what led us to discover that our universe is expanding. Okay, it's called redshift, where things are moving away from us, just like as something moves away from you sound wise, it's a lower pitch, it's a lower frequency. As something moves away from us at a really high speed, the light it emits has a lower frequency. Okay, and it turns out that the universe is expanding faster and faster, and some of these signatures are getting to the point where it's beyond our visible spectrum. So that's why that telescope they just put up, the James Webb, has a lot of infrared cameras on them to be able to see stars that are no longer visible.
We can have a star 2 years away.
Do what? We want to observe them. The space is expanding at a higher rate. We can't see them. They're just out there, but we just can't see them.
So we're just nosy, and that's why we're mad about it.
No, we want so the no. That's a great question. The further back, the further out we see, and we'll talk about this later towards the end of the year. The further back in time you see, and we'll talk about that. But that's why.
Wait, was space a certain
Dimension.
Yes, and
Yeah.
it's getting bigger, or
Yeah.
were we just really close together and now we're just spreading out?
Yes.
Really spreading out. Or is it like space?
No,
is small
it was
and
space.
it's getting bigger?
Space is small and it's getting
So
bigger.
both?
Space is we're getting it's spreading out, and like we're in that. Yeah.
But like, what is space?
Oh.
I really don't know. That's the thing that I'm just like, I don't never understand.